Welcome to Rewriting the Machine Learning Playbook. 50 papers, 1 day, breakthroughs from July 3, 2025. In this episode, we'll journey through the latest machine learning research, spotlighting advances in robustness, fairness, and interpretability. We'll explore how theory and application are shaping tomorrow's AI, with insights drawn from 50 papers published on a single day. Let's dive into the core ideas and pivotal innovations defining the new frontier of intelligent systems. In this guided tour, expect an in-depth look at 6 key themes currently driving progress in machine learning. Discover how emerging methods address fairness, efficiency, and safety, core issues shaping today's AI landscape. We'll also highlight 3 influential papers that are changing the field, connecting foundational theory with real-world impact. By the end of this episode, you'll gain a clear perspective on where artificial intelligence is headed next. Machine learning is the central engine powering modern AI. At its core, it teaches computers to learn from data, enabling systems to make predictions or decisions without being explicitly programmed for every scenario. This technology underlies chatbots, medical AI, self-driving vehicles, and much more. Major breakthroughs in artificial intelligence typically first emerge in dedicated machine learning research communities, particularly on platforms like the arXiv preprint server. Today's focus includes deep learning, reinforcement learning, and the pursuit of fairness. The field is continuously pushing the boundaries of what AI can achieve. Theme 1 centers on robustness, generalization, and fairness. The primary goal is to develop models that function reliably across diverse scenarios and user groups. Notably, the paper Fair Deepfake Detectors Can Generalize by Cheng and colleagues demonstrates a connection between fairness interventions and improved robustness in deepfake detection. In healthcare, advanced survival analysis models are now calibrated to ensure demographic fairness, reducing bias in clinical decisions. These advances challenge the traditional trade-offs between fairness and accuracy, ensuring that artificial intelligence remains trustworthy and equitable in real-world applications. The second theme addresses efficiency, scalability, and privacy. As data volumes and model sizes expand, the demand for faster and more scalable machine learning solutions has intensified. Technical innovations such as 2 simplicial attention mechanisms and new techniques for training recurrent models are significantly improving computational efficiency. Federated learning enables collaborative model training across distributed devices or institutions without centralizing sensitive data, while differentially private methods safeguard privacy. These advances make artificial intelligence practical for large-scale, distributed, and regulated environments. The third major theme is interpretability and representation learning. Beyond producing accurate predictions, models must be able to explain their decisions. One notable study by Baroni and collaborators challenges the necessity of layer norm during inference, opening new avenues for model transparency. Meanwhile, novel autoencoder architectures are being developed to disentangle complex data factors, and new tools are emerging to track model predictions over time. Together, these advances help both users and experts build greater trust in artificial intelligence systems. Theme 4 highlights reinforcement learning and decision-making. Unlike standard models that focus on classification or prediction, reinforcement learning agents are trained to act within dynamic environments. The Expo framework, introduced by Zhou and team, leverages self-explanation to help models unlock hard reasoning tasks. Additionally, language models are now being used to automate reward design, while Bayesian methodologies are making exploration more efficient. These developments significantly expand artificial intelligence's capacity to address complex real-world challenges. The fifth theme encompasses applications and theoretical insights. Machine learning is now being applied to an extraordinary range of domains, from medicine and urban planning to scientific discovery. Researchers are using AI to predict protein interactions across species, optimize urban bike-sharing systems, and design more effective antibodies. On the theoretical side, work such as the mathematical proof of the impossibility of perfectly safe universal approximators is reshaping conversations around AI safety. The principle of compositional sparsity offers a new perspective on why deep learning works. Together, practical applications and theoretical advances are pushing the boundaries of what artificial intelligence can achieve. Let's review key findings from this research landscape. First, the removal of layer norm from transformers, as shown by Baroni et al., simplifies and clarifies these models' internal workings. Second, fairness interventions, detailed by Cheng et al., are shown to enhance the generalization of deepfake detectors, contradicting long-standing assumptions. Third, self-explanation techniques, highlighted by Zhou et al., enable reinforcement learning to address previously intractable reasoning tasks. Fourth, privacy-preserving methods continue to expand the possibilities for federated learning. Finally, new theoretical work is establishing the boundaries for safe and robust artificial intelligence. Today's machine learning research relies on a diverse set of methods. Deep neural networks, including transformers and recurrent neural networks, serve as core workhorses for processing complex data. Reinforcement learning frameworks empower agents to act and adapt over time. Information-theoretic tools such as entropy and mutual information guide model learning and quantify uncertainty. Federated and privacy-preserving learning approaches facilitate secure collaboration without exposing sensitive data. Finally, explainability methods help demystify the inner workings of models, opening the so-called black box for expert and user scrutiny. Our first paper spotlight is Transformers Don't Need Layer Norm at Inference Time, authored by Baroni and colleagues. This research systematically removes all layer norm layers from GPT-2 models after training, including the extensive GPT-2 XL, and then fine-tunes these models for downstream tasks. The result is a negligible drop in performance, even for large models. This approach significantly simplifies the internal model structure, making interpretability more accessible. Direct logic attribution, a technique for tracing model outputs to specific components, becomes exact in these normalization-free models. The study is especially notable for challenging foundational assumptions in deep learning and for enabling a new level of transparency and analysis in large language models. The next featured paper, Fair Deepfake Detectors Can Generalize by Cheng and collaborators, demonstrates that fairness interventions can simultaneously improve model generalization. Using causal analysis and demographic-aware data rebalancing, the authors introduce the DADE framework, which consistently outperforms current state-of-the-art methods. This work shows that technical performance does not have to come at the cost of social responsibility. In fact, the two can be aligned. The paper is distinguished by its rigorous theoretical approach, practical impact, and relevance to the development of equitable and trustworthy artificial intelligence. The third spotlighted paper is EXPO, Unlocking Hard Reasoning with Self-Explanation Guided Reinforcement Learning by Zhu and colleagues. EXPO enables models to generate positive training samples by conditioning on ground truth answers, overcoming traditional reinforcement learning limitations on hard reasoning tasks. This framework improves both learning efficiency and performance on challenging benchmarks such as Level 5 mathematics problems. Modular and straightforward to implement, EXPO is readily adaptable to various domains. It has been selected for its novel approach and its significant potential to empower next-generation reasoning systems. Looking to the future, several research directions are emerging. Modular and interpretable machine learning architectures are gaining importance, as evidenced by the move toward normalization-free transformers. Automated reward design using tools like language models or Bayesian optimization could democratize access to reinforcement learning. Techniques for privacy-preserving and federated learning are expected to expand, driven by increasing data sensitivity and regulatory requirements. Ongoing research will also intensify its focus on robustness, fairness, and risk management. Crucially, the interplay between theory and real-world application will continue to drive progress in the field. This synthesis was produced using GPT 4.1 from OpenAI for summarization and narrative construction. Text-to-speech synthesis is provided by DeepGram, and accompanying visuals have been generated using Grok. All content has undergone human expert review for clarity and accuracy, though minor oversights may remain. References for all discussed papers are included. This production combines advanced artificial intelligence tools to deliver accessible, up-to-date research summaries to the AI community. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.